This is the Progress Check 3 homework video. On this progress check, the goal was to be able to solve quadratic inequalities using their graphs, and then to be able to express the solutions to those inequalities using inequality symbols, number lines, and interval notation. As you approach each problem, this is the thought process that you want to go through. You have to find the x values of the intersection points first, determine whether the inequality is indicating that the quadratic is higher or lower than the linear. Determine if the solution is split or connected, meaning is it outside of the intersection points or is it between the intersection points? Is it equal or not equal to, open or closed dots, round or soft brackets? All of those questions have to do with the type of notation that you're using, and it should all match the inequality symbol that was given in the original problem. And then how can you go about checking your solution? So let's take a look at this first example. First, we want to identify the intersection points, specifically their x values. According to the graph, the intersection points here are -7 and -2. Those are going to be the numbers that show up on all parts of our solution. Next step is to determine what the question is asking. In this case, it's saying that the linear is greater than the quadratic. Or another way to think about that is that the quadratic is less than the linear. Looking at the graph, we want to figure out if that happens between the intersection points or outside the intersection points. In this case, it happens in between the intersection points. That's when the quadratic will go below the linear. So this solution is going to be a connected solution. Next thing we'll do is write the solution using inequality symbols. Since this is connected, or it's between the two intersection points, we put x in between the two numbers, -7 and -2. With symbols that show that x can be greater than -7 but less than -2. And the type of symbol we use matches what's in the original inequality. So these symbols have no lines underneath them because the original inequality had no line underneath the sign. Next, we'll make our number line. We'll put -7 and -2 on the number line. We use open dots because there's no line underneath the inequality sign. And then we'll draw the line to connect the dots. And then the last step is to write it in interval notation. In this case, since it's a connected solution, or our solution is between two finite numbers, there's no need to use the infinity symbols. We would only need to use those if the solution was outside the intersection points and continued going towards negative infinity on the left side and positive infinity on the right side. But in this case, it's got a very clear start and end point. It starts at -7 and it ends at -2. So there's no need for the infinities on this one. Let's take a look at another example. First, we identify the x values of the intersection points. Then we determine what the inequality is asking us. In this case, it's saying that the quadratic is greater than or equal to the linear function. That's going to be another connected solution. It's between those two intersection points. So step 3, we'll write the solution using inequality symbols. This time, since our inequality symbol originally had a line underneath it, our inequality symbols here will have lines underneath them. And then we'll show x being in between the two values. Next is our number line. This time we'll use closed dots. And then connect, again, because we've got a solution that's in between the two intersection points. And then for interval notation, this time we're going to use square brackets because there was a line underneath the inequality sign. And again, we don't need the infinities because our solution has a very clear starting and ending point. It starts at -3, it ends at +1. This solution tells us that if we were to choose a value in between -3 and +1, or if we chose the values of -3 or +1, then that means that that would give us a situation where the quadratic would be greater than the linear. For example, if I chose a test value of x equals 0, that falls in between the interval that I just identified. It's a number that's in between -3 and +1. Shows up right here on our graph. If I were to plug that in for x on both sides of the inequality and then simplify that, I get a statement that reads 6 is greater than or equal to 0. And this is true. So that means that the interval that I chose, numbers in between -3 and +1, will work for this inequality. That's what makes the quadratic end up having a bigger result than the linear. Okay, let's take a look at example 3. First, we'll identify the x values of the intersection points. Then we need to ask ourselves, what does the inequality mean? In this case, it's saying that the quadratic is greater than or equal to the linear function. It's nice for us to have a graph to be able to identify where that happens. Using that picture is a much faster way of identifying when one function is higher than another or greater than another, as opposed to just plugging in a bunch of test values to figure out when it's higher and when it's less than. In this case, our solution ends up being outside the intersection points, so all of our notation will match what a split solution would look like. First, we'll write our inequality symbols. We want to say that x can be less than or equal to 0, or x can be greater than or equal to +4. This portion of the solution goes along with this part of the graph, and then this part of the solution goes along with this part of the graph. Next, we'll set up our number line, put the two x values on the number line, and we need to show that x can be less than 0 or x can be greater than 4. So in this case, our solutions don't have ending points on either side. One's heading towards -infinity and the other is heading towards +infinity. So with our interval notation, we will have to use the infinity symbols. This tells us that if we end up choosing any x value that's less than 0, or any x value that's greater than 4, and we plug it into the inequality, then we'll get a statement that's true. Alright, our last example. First, we'll identify the x values of the intersection points. In this case, we're looking at +1 and +6. Then we'll figure out what our inequality is asking us. It's wanting to know where the quadratic is less than the linear. In this case, that's outside the intersection points, shown by the highlighting on the graph. Next, we will set up our inequality symbols. We need to say that x can be less than 1, or x can be greater than 6. X being less than 1 matches with this part of the graph, and x being greater than 6 matches with this part of the graph. Next, we'll set up our number line. In this case, we're going to use open dots because there's no line under our inequality symbols. And again, we're heading off towards -infinity on the left and +infinity on the right. So in our interval notation, we're going to need to use the infinity symbols. Just as a reminder, this union in the middle is very important. It shows that there are two separate pieces of our solution, but they're both part of the solution for the same inequality. And again, this tells us that if we choose anything less than 1 or anything greater than 6 and plug it into the inequality, then we'll get a statement that's true.